So vectors are simply vessels of magnitude and direction. So what does that mean? This is a bit of a loaded sentence. Basically, vectors are representations of magnitude and direction. Now, in the mathematical context, or at least in high school, we are generally restricted to some xyz or xy direction. So in extension 1, you'd be used to xy, and extension 2, you'll be today introduced to xyz. But we'll talk about later on how vectors can be incredibly useful in different fields that go beyond just defining xyz into different categories like bias, weight, force, whatever, velocity even, acceleration. Scalars, on the other hand, are vessels of only magnitude. So scalars are going to be things that only carry magnitude. So this will be things like measurements of weight, like if I say I'm 50 kilograms, which I'm not, but if I say I am, there's no direction to that. There's only magnitude. So weight is a scalar. Something like your Valorant rank, your chess rank, your league rank, that's all going to be a scalar because there's no direction to that specific rank. I guess there could be a direction of how you're moving in that rank. And in fact, yeah, how you're moving in that rank could definitely be a vector, but your rank itself is always going to be a scalar. So what could be classified as vectors and what could be classified as scalars? Please drop some in the live chat, and I'll give you a thumbs up or a smiley face if you drop some good ones. So vectors, car moving. So this could be, I don't know, northwest, 15 meters per second. That might be a ridiculous speed. I'm not really sure. In fact, that is really fast, possibly very fast, whatever. In elevators, movement, stock prices, fluctuation. And then for scalars, we'd have recipe, measurements, anything weight related. Let's say mass, because weight is actually a force. So let's say mass. Sorry for any physics buffs out there who got offended by my use of weight before. And those are enough examples. Please drop some in the live chat if you want to. Okay. Notation and convention. Anyone who wants to do maths or engineering or computer science at university, please read this slide very carefully and understand me very clearly. Convention and notation is very important in mathematics. This is how mathematicians communicate, right? If I decided to say random words that kind of sound like English but aren't actually English to you, you wouldn't be able to understand what I'm saying, because English, the language, also has conventions and notations. If I wrote random letters that kind of look like English but weren't actually English or the alphabet, you wouldn't understand what I'm saying. So in the same way, we need to have a standardized way of representing what vectors are. Now, there are three main ways, but they're not always used equally. So the first way is a bold font. This is usually used in places like textbooks or typeset maths worksheets. The reason is because we have trouble writing bold font. Let's try. The vector. Yeah, it looks horrible. So my suggestion, don't use this one. At least when you're doing an exam on paper. We have the tilde, which I'm sure you saw in extension 1. Now, the most important the most used one for a tilde is just like a single letter. So when we have like a vector A, that's usually tilde, vector B, that's usually tilde C. But when we have two letters, which in extension 1 you might have learned, for example, in like a parallelogram, I don't know if I would be able to draw a good parallelogram. Let's see. That's all right. If we have O, A, B, C, then we have the vector OA, which is a position vector. You will probably not see OA tilde very often. What you will see is OA arrow, OB arrow, OC arrow, etc., AB arrow. And there are some textbooks and other people who like to use arrow for everything, so V arrow, A arrow. It really doesn't matter as long as for whatever vector you use vector notation, because without it, we won't be able to know what you're talking about. Okay? And try to use one convention in a question. Don't go hopping around between the 3 different conventions in one solution, because that just gets annoying for your marker, and the markers are the people we're trying to impress, so let's be nice to them. All right. So the geometric representation of a 2D vector is simply an arrow, which is a direct line segment between 2 coordinates on a 2D plane of a starting point, which is the tail, and a terminal point, which is the head. We can specify a vector geometrically going from O to A to the notation OA. So to recap, the starting point is the point on a vector without an arrow. So that's our starting point, and then the terminal point, which is where our vector terminates, that will have an arrow. And that is how we represent a vector geometrically. Just a note, as we transition into 3D vectors, graphing becomes quite difficult. As an example, I will try to draw you a vector. Now, where is this vector going? Is it going directly left? Is it going top rightish, coming into the screen? You don't really know. So a thing mathematicians might do is they'll draw something like that. Then it's a bit more clear that it's coming out to the screen. But in extension 2, you generally won't be asked too much about drawing vectors. In fact, in the plethora of trial papers and HSC papers that I did, I can't really remember a single time I was asked to sketch a vector. So don't worry too much about that. Don't worry too much. And if you are the vector, the drawing shouldn't be that difficult. Okay, now magnitude convention. So again, this is some extension 1 revision. The magnitude or length of a vector is written as the absolute value of a vector. So if we have a vector from extension 1, v34, then that's equal to 5. And just quickly reminding that for a vector v with components, with an x component v1 and a y component v2, the magnitude of the vector v will be v1 squared plus v2 squared. And we'll prove the 3D vector version in a second. And the 3D vector version of this would be, so if v equals v1, v2, v3, then the magnitude of our vector is v1 squared plus v2 squared plus v3 squared. Obviously, since it's just length and not a direction, it's a scalar quantity. The direction a 2D vector points to is measured by the angle it makes with the x-axis. So what that line is saying is, this is some extension 1 revision again, but if we have some vector v, then we can represent its direction with this theta that it makes with the x-axis. Okay, negative vectors. Negative vectors are very simple, but they'll actually be very important in proofs. Later on, we're going to do a very hard question at the end that negative vectors will be very important in. but we'll talk about that later. So here we have two vectors u and v. Now, they both have the same magnitude, but opposite directions. So u is the same as negative v. As if we made it negative, this would flip over to this side. So this is going to flip, and then, oh, that's a bad drawing. Going to flip, and the arrow would point at the same direction, therefore becoming v. And v also equals negative u. Yeah, so there's some polarity there. All right, in Maths Extension 2, we'll be required to visualize and manipulate vectors in three-dimensional space. The 3D plane is usually described by x, y, and z, where z points upwards, and generally x points towards you and y points to the right. So generally it's going to be z, x, y. Okay. We've learned a lot about vectors, but we haven't really learned why. And at least for me, especially in the HSC, when you're learning all this really dense content, it's really helpful to know where these things are being used in. So before we learn all the applications within mathematics, it's important to ask why we even need to learn what vectors are. So vectors are incredibly useful in lots of fields, including computer science, engineering, and economics, and they're used in physics and engineering to represent forces. So computer science, which is what I study, we all know ChatGPT. I'm almost certain that ChatGPT would take advantage of vectors to figure out proper pathing for their responses. It's obviously very complex. In artificial intelligence, we have things called bias and weight. And so we kind of break beyond these barriers of X, Y, Z. So instead of just representing some three arbitrary axes, we instead have, I don't know, maybe bias, weight, acceleration. And computer scientists use these new vectors to, one, perform very fast calculations, because vectorizing things makes calculation very fast, and get very useful results like ChatGPT. In engineering, the physics students out there have done vectors, or at least a little bit of vectors. Forces are vectors. They are always represented as vectors. It always has a magnitude and a direction. Lots of things in physics are represented as vectors, both in the definitional sense of the fact that it has a magnitude and a direction, but also geometrically representing things as arrows pointing somewhere is a really important outcome per se. Economics, I'm sure the economists at the Reserve Bank are talking about the movement of inflation. That could also be represented in vectors. If we look at the next slide, there's different scenarios here. So, if this is a door I'm trying to pry open, this is my pry bar. My pry bar is going to apply a force upwards, and then maybe a lock will be in place, and then this lock is trying to resist that motion. And that would all be figured out with vectors. So obviously in that case, if the force of the pry bar is greater than the resistive force of the lock, then the pry bar will open the door. Can the skyscraper stand after facing heavy wind? You can imagine winds can be represented as vectors, like that. Can you hear the music at the far ridges of a concert hall? A really cool thing about concert halls is that there's actually lots of engineering that happens to them. If you've been to a nice concert hall and you look around to the roofs and the walls, you'll see lots of weird cut out walls. What that is a bunch of acoustic engineers had to shoot out a bunch of sound waves and figure out how the sound is bouncing off of the walls. And then they had to fine tune everything such that for each audience member, they try to maximize the value of the sound they get. And obviously you can imagine this vector is going to be like bing, bing, and then if you're some audience member here, we generally want that vector to be redirected to your ears. And they're used in search engines. So let's say your search will have multiple different criteria, relevance, time, category, whatever. And then Google might use some sort of algorithm to check what's the closest result to this vector, and then they'd serve you that search result. Dating sites would be very similar, but with people instead. Game design obviously uses simulated physics, so that's all vectors. In fact, if you look at game engines, those of you who watch or who play Valorant, even the guns falling, that would all be done using vectors. Weather analysis, all the meteorology stuff, the barometeorology. If you look at the radar maps, I think if you zoom in, you might actually see some vectors. But yeah, lots of reasons why I use vectors. Enough of the yap. Back to the material. All right, 3D vectors. How can we represent them? Again, convention, notation. Super important stuff. A coordinate point on the 3D plane can be represented by an ordered triplet such as x, y, z. So a point in itself, so the point, let's say A, would be represented as, 1, 3, 2. A vector can be represented by column vector notation such as x, y, z. So the position vector, which I'm sure you learned in extension 1, here would be represented as 1, 3, 2. So these two are two different things, so you need to make sure you have a way to differentiate them. Okay, traditionally on a 2D plane, we only had 2 unit vectors. So unit vector, what is it? It's a vector of magnitude 1. Now with the introduction of the z-axis, we now have 3 standard unit vectors. So you can imagine when we had the xy plane, our unit vectors were just 1y, 1 towards the direction of y, 1 towards the direction of x. And you might have heard the term basis vectors. Now, in a nutshell, to explain it to high school students, basis vectors are a set of vectors such that they are able to span the entire set of points. So basis vectors have some restrictions to them. So a trivial outcome would be if there are n different dimensions, then there must be at least n different basis vectors. Now that makes sense intuitively. I won't go through the proof of that because that's university level, and you'll be going through this if you do any sort of engineering or STEM field in university. But yeah, it's important to know what basis vectors are. So now in a 2D plane, we have 2 dimensions, so we have 2 different basis vectors. But you could have 3 basis vectors or 4 basis vectors. So like if you have 1, 0, 0, 1, you could tack on 1, 1. And that would still be a set of basis vectors because you could still travel all of the points in the 2D plane. In 3D, we need at least 3 vectors, so that becomes I, J, and K, which just are all one step to each of the axes. Now, why they're called basis vectors? Because you're able to span it, and you span it using a linear combination. So these are some just useful terminologies that you might use during proofs. So linear combination would be any combination such that they are multiplied by a constant. So with any linear combination of I, j, and k, we can reach any point in the 3D plane. I guess the 3D area, 3D dimensions. Like for example, if I wanted to reach the vector 3, 1, 1, then A would equal 3, B equals 1, C equals 1. If I wanted to reach 0, 0, 0, then obviously A, B, and C would equal 0. Cool. If you need any clarification on that, ask below. This isn't mandatory to know all the basis vector and linear combination stuff, but it's really good to know, and it shows a good depth of information for the later geometric proofs that we might need this for. And here we have GeoGebra, so a tool I really recommend because it can show you really good geometric information about vectors. So here we have 1, 0, 0. Here we have 0, 1, 0. And here we have 0, 0, 1. Awesome. Geometrically, when we add vectors together, we place them head to tail. So that's gonna look like this. So let's say I have a vector A and a vector B. If I wanted A plus B, then I'd get A, tack it onto B's tail. And then A plus B would be from A's tail to B's head. I'm sure you've learned that in extension 1. This applies to 2D and 3D vectors, and if I remember correctly, this should actually apply in all dimensions, because this should be the definition of a vector addition, but I could be wrong. If I'm wrong, don't worry, because we're only going to be dealing with 2D and 3D anyways. But yeah, this outcome is very important later on for geometric proofs, so make sure you've got this remembered. When adding vectors algebraically, we add them component-wise. So in extension 1, you were introduced to component addition. Now in extension 2, nothing's really changing. We're just adding an extra component. So you can just think of it like this. And that becomes x1 plus x2 plus y2, z1 plus y2. And for subtracting, it's the same. Here, the working out that I've given actually converts this subtraction into an addition of a negative vector. So this is kind of important just for geometrically thinking about if I consider this A and B. It's kind of hard to imagine what A minus B will look like, but it's really easy to imagine what A plus negative B will look like. So if any of you struggle with, some of the questions that ask, what is A minus B, like in a multiple choice question, thinking of it as, instead of subtraction, you think of it as an addition of a negative, that might help you a lot. Okay. And multiplying a vector by a scalar is handled the same in 2D and 3D. So extension 1, you would have seen, where lambda, so where lambda is some real number, this becomes lambda x1, lambda x2. And yeah, and this will become useful in parametric equations.